Welcome everyone. This is the 15th part of my CH32 microcontroller tutorial series, and in this video I show you a basic communication between two CH9141 modules. This is also a bit unusual video compared to the rest of my CH32 tutorial series, because it is not about a specific CH32 microcontroller or its feature, but it is about an external hardware, and this is very similar to my TSL2591 light sensor project. I have a specific project in mind where I need a low power wireless connection, essentially used as a remote controller, and before working on that project, I thought it would be a good idea to work on the basic principles of this CH9141 chip and publish a video and article about it. In the video, I'm going to use this module, and it is very cheap, as you can see it. It's like $4 US, and it's a very simple circuit. And I put together already the demo circuit. So I put everything in a breadboard, and on one side, which is the sender side, I have a CH32V006K8U6 development board. This is my own development board that I developed myself, and this will be used as the host or master. And then on the other side, on the left side, I have a CH32V003 F4P6 microcontroller board, and this is just a simple AliExpress module, but it is also connected to a Bluetooth module, and it will be used as a receiver or slave in this configuration. And the wiring is very simple, and the reason why I chose my own microcontroller board is because it has two USART ports, and one USART port through a chip is opening a communication channel towards my computer, and then the other USART port is free, and I'm going to use that with the Bluetooth module. And I use an additional GPIO pin because in order to switch between transfer mode and AT mode when I send commands to the Bluetooth module, I have to change the AT pin on and off. And on the receiver side, I don't care about serial communication towards the computer. The receiver will only communicate with the Bluetooth module, and in addition to that, I also added an LED to one of the GPIO pins, and this will be used as an indicator to show that the transaction was successful between the two devices. So the receiver received a message from the sender or host. The device has a good datasheet. I put the link in the description, so please read it. It has all the commands and everything that you need, so read it carefully. Immediately the figures here show us the possible use modes. So one is that when we have, let's say, third device, a computer, mobile, or whatever here, or a serial port, and then that sends something to the CH9141 module, which then throughout the UART communicates with the microcontroller. So for example, you are sitting in front of your computer, you are connected to this device, which is here on the right side via Bluetooth. And for example, you can switch your light on and off by having a microcontroller and a relay connected together. And then that will be your remote for the light. Or in the figure 2, you can see that you have two identical, basically mirrored devices. So one pair of microcontroller and CH9141 module is on the left side. Let's say that's the host, and then on the right side we have the same, and that's the slave or receiver. And that's what I have on my breadboard assembled. So let's say on the right side you can imagine that I have the red microcontroller board, and on the left side I have the blue microcontroller board. In the datasheet, I want you to focus on one specific section, which is section number 6, because this contains the AT instruction set, and that is basically this table here, and this is the most important. You will see it when I show you the code, that we have all these AT commands that we can send to the Bluetooth chip, and then we can set different parameters or inquire different parameters. So for example, the 12th line is the MAC address inquiry command. So when you send this specific command with a question mark at the end to the Bluetooth module, then the Bluetooth module will send back the MAC address of the device that is connected to the microcontroller. And actually this is one of the most important commands, because in order to be able to communicate with the receiver, we have to know its MAC address. So then the host can reach this device by knowing its MAC address. So now again, I break my habit and I'm not typing the code in order to save time, but I'm showing you the already typed code, and then I explain what is happening and why it is happening. So there are two codes because we have two devices. We have a receiver and we have a sender. And logically, it makes more sense to work with the receiver first. So I will explain that first. So what we have to know is that we have to define a size for the receiver buffer. So this will be the number of bytes that the receiver buffer array can store. And I just set it to 64 bytes. That means that we can receive 64 characters. And then I already have this rxbuff, and inside the parentheses we have the size variable. So here I defined a variable, an array which can hold 64 characters. And then I have a counter which keeps track of the indices, because when we fill up the arrays, then we have to advance the number of the indices, and we also have to keep track of them. So that's that. And then this is a very typical USART configuration. I have a tutorial video on USART, so everything is explained there. So I will just go quickly through this code. The most important thing is that I'm using the F4P6 development board, and that has its default USART pins on PD5 and PD6. Now, as you can see that the GPIO mode of the PD5 is defined as AFPP. So that's the alternative function because it's a USART pin now, and PP means push-pull because this is the TX or transmit pin, and that has to be pushed or pulled because we set it with the microcontroller. And on the other hand, PD6 is set as floating because this will be dragged high or low by the device that is connected to it, because this is the RX pin, so this is the receiver pin. And then we have the basic settings for a typical USART communication. I'm just using the default USART rate and the word length and everything, so there's nothing needed here. And then I just enable the USART in this function. Then, as I said, there will be an LED on this device to indicate something. So I define the PD3 for that. So we have the GPIO pin 3 on the port D, as you can see it here. And it's a push-pull output because we want to be able to toggle it. And then I want to jump down to the main code because it makes more sense to show what is going on here in the while loop. And then I can explain the corresponding functions better. But what's going on here is that I'm polling the serial port here. So I'm just constantly reading if this flag is set. And then when this flag is set, so there is something to read from the register, then we enter the rest of the code. So what we do is that then we receive that data from the USART1 and put it in this received byte. And we store a byte which is 8 bits, but this can receive 16 bits, as you can see it in the description. So to avoid garbage data, we just use the logical AND operation here with the 0xFF to just keep the proper bits. And then what we do here is that since it's a serial communication, we can have two characters at the end of the message, and one is the R or carriage return. And if we receive that, we just jump through the rest of the code. Or if we receive an N, which is a line feed or N-line character, then we jump into a function which will process the line, because this single character here basically indicates the end of the message. In this protocol that I explain here and I developed here, each message is just one line and it ends with this line break character, which is highlighted. So there won't be any multiple lines, so I can rely on this type of communication. So we process the line, so I will jump to that function soon. And then we reset the counter for the buffer. And how we do that is that we set this RXI to 0. So then when we start to write in the buffer again, we will start writing from the first position in the buffer. And because we filled up our received byte variable, if that received byte is none of these two here, so R or N, then that was a regular character. So if we are within the bounds of our buffer, that's what this if condition means, then we just put this received byte into the corresponding place in the buffer. And then with this plus plus, we also advance the value of the counter for the index. So in the next iteration, then let's say we were at the first position, we will write in the second position. And then if we reach the maximum capacity, so if this is not true, so we somehow end up in this part, then we reset the buffer, so we just discard whatever was there, and we send to the USART1, which is the Bluetooth receiver, which will then send the message to the sender that there was an overflow error. And regarding the process line function, I can jump there, and what we can do is that we check if the message was for some reason 0, then we just ignore everything. And then we null terminate our buffer here, because the RXI is still not 0. It's at the whatever item which we wrote into the buffer. So then we put a 0 at the end. And then what we do here is that we check if the first item inside this buffer is an exclamation mark or not. If it's an exclamation mark, then we proceed forward, and then we check if the message is more than 2 characters, or at least 2 characters, because otherwise it would not make sense if we would just send a simple exclamation mark to the receiver. So if it is, then we check the next item, so the character which should be after the exclamation mark, and put it in this CMD variable. And then I just implemented a simple switch case, and I do different things. So if I send an exclamation mark followed by a capital A letter, then I just simply toggle the pin 3 on the D port, so PD3. And I send back a message via the Bluetooth to the sender. So this will be simple. And how this line works is actually quite fun. So we read the recent output data bit from the register, which corresponds to the PD3, and then we invert it. That's why this exclamation mark is here. So if it was 0, then we will set it to 1. If it was 1, we set it to 0, and that's how we toggle it. And then I created, let's say, a simulation or a mock-up weather station. So I have T as temperature, H as humidity, and P as a pressure. And then if I receive exclamation mark T, then I send back this message. If it's with an H, then I send back this message. And if it's a P, then I send back this value. And yeah, of course, I don't have the device put together with the weather station, because that would be extra coding and extra explanation needed. So I just send back some dummy values just for testing. And this is also a good proof that the communication is two-way, because the receiver had to receive the command and then it has to send back. And then this should pop up on my serial port, which we will test very soon. And then if none of these messages were sent, then we just send back an error that, hey, it's an unknown command. And here in the beginning, we were asking for at least 2 characters. So if that did not happen, then we say that, hey, the command is missing. And then if the first character is not an exclamation mark, then we echo back the whole line that we sent to the receiver. And this is again just a test for the two-way communication. So first I indicate with a text that this is an echo, and then I actually send back the content of the RX buffer, the whole stuff as it is, and then I send the R and the N letters back, so the carriage, return, and the new line characters, to basically encapsulate the message. So from here we can go to this send USART1. And this is very simple. We just have a pointer for a string of characters. And what we do is that we iterate through those characters which are passed to this function. And then in each iteration, we wait until the transmit data register, TXE, becomes empty. So the recent stuff got sent out. And then we send out what we have now. And we have the pointer. So we send out that specific character that the pointer points at. And then we increment the pointer. So when the next iteration happens, then the pointer points at the next coming character. And then when the pointer hits a null terminate character, I wrote it down here, then this while condition makes the function to not return anymore. So everything is concluded here. And you can see that this send usart1 crlf was there right under these functions when we echoed back the whole message. And that is just this. So it's a /r/n to encapsulate the message according to the Bluetooth communication protocol. And well, that's the whole code for the receiver. So now we can go to the sender, which is a bit more complicated. So we arrived at the sender code, and the beginning is fairly similar. So we have a max value defined for the buffer size, and then we define a buffer with that maximum size, and it has to be volatile because in this code I will use interrupts for the usart or for part of the usart. So therefore we have a few variables, also the counter and the rxdone variables, which have to be defined as a volatile variable. And then we have a non-volatile character array, and this will be used to fetch the data from the buffer and store it. So we create a copy, and we will work with this line array. So as I said, this microcontroller has two USART ports. So the default here is still the same, PD5 and PD6, so TX and RX, this is same. And I left everything at the default. But we have another USART2 here, and this requires a little bit of reading. So here what I do is that I remap the pins of the USART, and what I do is that I make the PD2 pin as the TX that you can see here, and I make the PD3 as the RX. Everything else is the same, but how this is done is the following. So we have this macro, and you can see that here the character before the last character is number 3. Then we open the datasheet of this device, and here in the USART2 alternate function remapping, we can see that when the bit value returns 3, then we have the TX at PD2 and we have the RX at PD3. So that's how you can read which macro you should choose. So obviously this would be for the first partial remap. This is the second, third, fourth, fifth, and this is the sixth. And this is actually a full remapping, not just a partial remapping. So yeah, I chose this here. And then that's what I use here. So you can see that partial remap. And why I highlight that 2, 3 and so on is because you can see that both USART1 and USART2 has separate list of remap macros. So we can choose whatever, but yeah, I stick with the USART2 remap 3 option. And then here I also added a part which belongs to the interrupt. I have a separate video on interrupts as well, so please check it if you want to understand more. But the only thing here is that, yeah, I just added the USART to the interrupts, so I will be able to use the USART, especially the reading part, with interrupts. And then a little bit jumping back, we also have one single GPIO pin, which is an additional GPIO pin, and that is PD4, which will switch the AT pin on the sender Bluetooth module high or low, because based on whether it is high or low, we can use transfer mode or AT command mode. So we can send commands and configure the device, or we can just communicate with the receiver. So similarly to the receiver code, I jump to the while loop, because from here I can work my way towards the functions, and I can explain everything hopefully in a more structured way. So we are polling also not only using interrupts. So for example, this is actually polling the buffer which is made by the interrupt routine. So I created a function that takes the USART2 buffer, so the Bluetooth module's buffer, and puts it in this line character array that I explained a minute ago. And then it's just very simple that if it is not empty, then we print the line with this printf command. So the actual content of the line is this %s, and then here is the line referred, and we just printf it because we print it on the USART1. And then I have to rearm the interrupt, so I have a separate function for that. And then we want to communicate with the Bluetooth device via the serial port. And how we do it is, again, we are polling. So we check if there is a byte waiting in the USART1, and if that's the case, then similarly to the receiver, we receive it into a byte-sized data variable. So we chop off a few bits here and there with this 0xFF and the logical AND operation. And then we wait until this transmission is concluded, and then we send it to the USART2. So as you can see, with this part of the code we receive from USART1, you can see that we are waiting for the RXNE, or receive not empty byte. So that is the receiver, and this is coming from the PC. And then we send it out to the USART2 with these two lines. So we wait until we can put things into the transmission register, and then we send out the byte that we received from USART1, we send it to USART2. And then this is in this infinite loop. So as long as we have bytes in one of the USART ports, they will be sent or received, because this goes on and on continuously. And then I can jump to this USART part, which is the USART2 interrupt handler. And then if there is something to read on USART2, so the receiver sent back something to the sender, then again, we read out that byte directly from the data register and put it in the received byte variable. And then we check if the line is not completed, so this is false, then we check if we are still within the capacity of the buffer. And if it is so, then we add this byte to the corresponding position inside the buffer. And we advance the index of the buffer, so next time we write to the next place and so on. And then, if we are not done yet, but the received byte is n, or we are at the boundary of the capacity of the buffer, then we say that, okay, we raise the flag and the RX is done, so we don't accept any more stuff in our buffer, and we disable or disarm the interrupt. So we are not able to fill anything more into the buffer. And when that buffer is done, we can copy it to our line buffer, if you remember from the beginning. So we just check if by some chance, if it's not done, then we return. So we are still receiving data in the buffer. And otherwise, we check the number of bytes inside the buffer. So this is just how we count it. So you can see that what we do, this is actually an if-else block here. So if we are below the destination size, -1, because of the null terminate, we have to go -1, then we return this value, so the count itself. Otherwise, we reach the maximum value, so we have the destination size -1, because we still have to add the null termination to the end. And here I have two options. One is this mem_cpy, and what we do here is that we have the destination buffer, which will be the line buffer passed to the parameters up here. So we copy to here, from here, this amount of bytes. Or Similarly, we can do the same with a for loop. I just left this here. You use whichever you like more. And so we went until destination size -1 when we fill in the nth item, so one item after the n-1, we put the node terminate character at the last position. And also optionally, we can strip this CR or LF tail from the message. And that's how we do it here. Again, just some condition with some logical operators. So if it's the n and whether these characters is true, then we place the null termination to that corresponding position. And then finally, this function will return with the final length of the whole destination buffer. And just to make sense, so now if I jump back to the while, so you will understand that this is the function that I recently explained. And then, as I said, it returns with the number of items in the buffer. So we will have that in the n. And then if the line is not empty, so if this is not 0, we enter this block. And then we simply print with the printf the contents of the line. And that will show up on the computer. Then I can explain this part where we can initialize the Bluetooth. And here we can do different things. But what we can do here is that, as I said, we have to enter the AT command mode somehow. So that will be done by pulling the PD4 pin to low. And then I wait a bit for settling. And then I arm the RX, so the receiver buffer. And then I send this string to the Bluetooth device. So this, since we are in AT command mode, just goes to the Bluetooth device. The Bluetooth device is not communicating with the receiver at this moment. And then we just send a hello message, and then the Bluetooth device should send a response back to the microcontroller. And what we do is that I have a function for that will wait for this, and it will print it on the serial terminal of the computer. So before advancing down, I want to jump to this function and explain it how it works. So here we wait until the buffer is full. And we can wait here with an infinite loop because the buffer in the meantime is filled through an interrupt. So when the interrupt wants to deal with the data, it will do its thing. And then it will change this u2_rx done to true when the buffer is full. So then the code will advance to the next line, and I just simply printf the contents of the buffer. So I don't even copy it in this part. I just print it, although I could use the previously introduced function here and copy it and print it, but in this situation, before the code is running continuously on the microcontroller, I can use this without breaking anything. It can happen that sometimes the microcontroller receives some garbage from the Bluetooth device, because the Bluetooth device not only can send back the response to the inquiry, but sometimes it sends a, let's say, a confirmation message, which can be a few line breaks and an OK or something like that. So I want to clear that out from the receiving buffer. So I do that with these few lines. So what I do is just, I simply wait for a few milliseconds, which is defined in the parameter of the function, which we passed to it. And that was 120 milliseconds. So we wait, and then we just rearm the buffer. So we empty it and put the index back to 0 and so on. So whatever arrives to the buffer in this 120 milliseconds, or whatever we define, but we have 120 here, that is treated as garbage and it's thrown out. And then once again, we have to rearm the receiver to get rid of everything for once. So coming back here, we can inquire the Bluetooth mode. So this is the BLE mode. And I just put here what it can be: broadcast, host, or device. And in our case, this will be host. So it should respond with 1. And then we can ask the name. And I will receive sender, because that's what I named the device. And here this is what I said, that we need the MAC address of the receiver. So I already pass this to the sender device, and then the sender should return a message with number 3 when I ask the Bluetooth status, which indicates that the connection is successful between the two devices. And then also as a example, because that will be needed for the receiver, I show how to ask the MAC address. So this code actually has to run on the receiver, or actually on the receiver Bluetooth device, to know its MAC address, which is this in my case. And then we can go to the beginning of the main code. So we configured the two USART communications, the GPIO pin that takes care of the AT pin. And here I want to show you a few things. So I will switch to my terminal. So here is my terminal. And just to be sure, here is the setup. So we have the sender here, and it's connected to the Bluetooth device. And we have the receiver here, and that is also connected to the Bluetooth device. So everything is fine so far. And I'm just going to trigger some response from the receiver so we can see how this thing works. All right, so I arranged the windows so you can see everything. And in the meantime, I also remembered that I should connect the programmer to the microcontroller, because that's the easiest way to trigger a reset. And I want to trigger a reset so I can show you the code, especially this thing in the background when the microcontroller is booting up. So everything is set up, so I just upload the same code again. So here is our message, and I can just scroll so we can see that the response to the hello is welcome, and then the Bluetooth mode is 1, and then the name is sender, and then we are trying to connect to the receiver, which is under the MAC address, which is in the background. So that is returning us a 03 Bluetooth status, which is good because that means that we are connected. And then we inquire the MAC address of this device, the sender device, and that is here. And then finally, we reached this message in the background, this printf message, and that is showing here. So now what I can do is that, for example, I can send a message to the device and hopefully it will work. So I just type in something garbage. I press enter twice because I noticed that sometimes it doesn't work if I don't do that. And then I just send this to the Bluetooth device. And you can see that an echo showed up. I should turn on the auto scroll, and that quite much resembles the message that we have here. And then I can send a more complex and more readable text, and we receive it back. Now we can have this !T, which should send back the temperature data, and we get back that. And then we had H as humidity and P as pressure. Everything comes back from the receiver as we pre-programmed it, so that's very nice. But what is cooler is this. So I want you to focus more on the LED, which can be found here. And if I send this, tada, we toggled the LED. We got back the message, and you can see that the red LED right there turned on. And if I send one more message, then I turned off and I got the message that it's toggled. So that's pretty nice. And if you remember, we had some error messages. Let's try to trigger them. So I just send a single exclamation mark. And then now we got the message that the command is missing. Or I can send an exclamation mark E. And well, that's an unknown command, so that doesn't work. But if I send the message again, then I get it back as an echo because it doesn't contain any exclamation mark in the beginning. So it works. So this is a two-way communication, and it is between the sender and the receiver, so it works very well. And you can see that the implementation is fairly simple. And just one thing that I want to show you that is in the background. So I remove these, and then I uncomment this part of code. So what I want to show you is that we can modify the name of our device. And for example, I will call it as a demo device. So what we do here is that we set the device into AT mode, and then we change its name, and then we ask its name. And then I also want to show you that certain parameters need a reset to apply them. And that is, for example, the Bluetooth mode, because if I set it to 0, currently it is 1, I can prove it, because the Bluetooth mode here is 1. If I set it to 0 and I ask it again what it is, it will still return 1. So I compile this code and upload it, but before I erase the terminal, and now we applied the name and it is demo device, but the Bluetooth mode is 1, which was the previous. So the 0 did not get applied. So how do we get it applied? So I show you. I take this line because I just want to send another command, and I just put it here and we name it to reset. So we need to reset the device. So I compile this and upload it to the microcontroller. And now, as you can see, I get a bit of a garbage message because the Bluetooth mode doesn't show up, but it just sends an OK. However, I can remove these lines now because I don't need them, and compile. And now, if you remember, this was our previous set of responses, but now we have still the name, and now the Bluetooth mode is 0. So we successfully modified this. And if we want to change it back, then I just add these lines back, compile and upload. Again, nothing shows up, but I compile and upload again, and there we go. So now I could remove this code, compile and upload again. And if you look at the terminal, I can go down, you can see the welcome message, which comes from the hello. And then we have Bluetooth mode 1, name is still demo device because I haven't changed it. We are not able to connect to the receiver because we have Bluetooth status 2. And then we have the MAC address as well. So therefore, we have to still change something here. And I just had to re-upload the code again to trigger one more reset on the device. And now we have Bluetooth status 3. And just to check if it works, here's the camera. I turned it back and we just send a random message and we got it back. But to show that this is live recorded and everything, there is our toggled light. Auto scroll can be on. So we see that the message is coming in. And this should also work. And then we got the temperature as a response. So everything works. So now we know how to establish a two-way communication between two microcontrollers, and we know how to communicate back and forth. So this will be a very interesting project for anything that you want to build with a remote control or with a remote station, because this Bluetooth device has up to 100 meters range. So you can have this thing inside your house and you can have some sensors outside the house and you can still get connection between the two devices, or you can have sensors scattered all around your apartment or house, and they should be able to communicate with each other. So you can have a central unit and then you can broadcast data to that central unit from several slaves, for example, which could be an interesting project for thermometers around your living area, for example. And for my case, I have a specific application for this remote controller project. I actually won't need these very fancy microcontrollers, so I will just use the most basic microcontroller because I don't even need serial communication and similar things. I just need something that can change a GPIO and detect a change on a GPIO, so basically a button-based remote. And I will base it on these Bluetooth devices, and actually I will hack a certain machine or device so I can turn it on and off remotely without any kind of physical connection. And hopefully, if everything goes well, I can operate the remote controller from a battery, and hopefully the battery will last for maybe years. We will see. So I wrote a very detailed article about this topic, so please visit my website, the link is in the description. And if you want to get the code, then as usual, I shared the whole code both for the receiver and the sender on my GitHub project for the CH32 microcontroller tutorial series. So this is the 15th part, so please check that specific folder. The link is in the article on my website. And then you can get the code and expand it and improve it if you want. And if you like these kind of tutorial videos and you want me to produce more and you want to encourage me, please consider becoming a member of my channel, because it's not only that you can get some extra perks, but you can also support me so I can spend more time and obviously more money on these kind of projects. So for example, I can buy these kind of modules and I can develop these kind of development boards. So it's a win-win situation, I think. So I hope that you like this video. I hope you learned something, and see you in the next video.